And Eric, many of you may know from 1996 when he was a member of the Johns Hopkins Summer Workshop team on pronunciation modeling. He has since completed his PhD from University of California, Berkeley. He's affiliated with the International Computer Science Institute. He has a degree from the University of Pennsylvania, summa cum laude, and great pleasure to have him.
Right. Well, thank you for inviting me. I'm really excited to be here because I know everybody here takes language and speech very seriously. So despite that, I'm going to actually try and motivate why we're still working on speech. Because it's good to be reminded why it is that we're actually working on these things. So one thing we should start off with is what can we do at the moment, and what real systems do we see out in the world? Well, one thing that you can get nowadays is you can get your flight information over the telephone. Say you call up United Airlines and you say, I want to know when flight 1723 leaves from Chicago, and it will tell you these kind of things. So these types of tasks give you a very small vocabulary, and we can, because the domain is very restricted, we can do very well on these things. When we move out to larger vocabulary tasks that people are actually, when people say speech recognition, this is often the first application that people think of, is dictation tasks where they have people writing letters, sitting down at the computer and writing a letter, and they may have repetitive stress injuries or something. We have a large vocabulary, but we restrict the tasks in other ways. So, for instance, we make sure that people are wearing a close talking microphone mounted on their head usually. And we also train and adapt the models to be for a specific speaker. So we don't have speaker independence. And there are other tasks that you can see. But I think an important thing to recognize is that that we really want speech to become a primary interface for a lot of applications. So for instance, if we want to be able to go back and forth between telephone applications like voicemail and email, that's going to require speaker independence and large vocabulary. If you want to use one of these PDAs that are becoming really popular, right? These have, the ones that are coming out now, like the handspring visor, have really low quality microphones. So that's an issue for being able to use these things. And if you want to, say, put it down on a table and record a meeting and then later transcribe it, you need to be able to deal with things like room acoustics. So one can, sort of go down the road of, what's the more fanciful things that you can come up with. So maybe you want to be able to control the lights in your house, or maybe you have clothes that will do, record reminders or something like that. But I mean, in essence, the most extreme is, Star Trek, right? So I'm going to use Star Trek as an example of, what is it that we can't do? So for those of you who don't know Star Trek, the captain stands on the bridge of the Enterprise and they say, computer, tell me, what the distance to planet X is, right? And this, one thing that's very important that we don't really understand a lot about is application interfaces. So how does the computer know when you're talking to it, and how does it know when you've stopped talking to it? So that's an important area of research that we need to look at. Also, as you're moving to more and more natural situations where you're interacting with the computer a lot, you are going to be talking more naturally to the computer. So now, when we do this nowadays, we actually, for large vocabulary tasks, we're getting at least 1 word in 5 wrong. So this is for like recording broadcast news, reports off the TV, and we're still getting like 1 in 5 words wrong for spontaneous conversations. And there's a large number of reasons that I've sort of touched on already about reverberation, where if you don't have a close talking microphone, the echoes will bounce back and you get multiple recordings of the same sort of speech signal. Background noise is very prevalent, so in more natural conversations. So like the lamp of this projector here is, or the fan of the projector is creating some actual background noise. Speaker independence, as I touched on, there's this trade-off between speaker independence and large vocabularies that we have nowadays. Another major thing that we don't know how to do completely yet is confidence. So knowing when you're right. So if the computer, if in the situation where you have the constraint test, like the flight information, if you say, I want a pizza, right, the computer knows enough to reject that. But as soon as you start opening up the vocabulary, things become very difficult to reject. How do you know when you've got something that just fits outside, is outside the domain? So finally, one of the important things is that we don't know how to deal with different actual linguistic differences in the speaking style. So I want to show a quick example of spontaneous versus planned speech. So this is looking at those newscasts that I was talking about, but comparing the newscasts where the newsreader was reading the transcript off of a teleprompter versus when he's interviewing somebody in the studio. So the acoustics conditions are exactly the same here, but it's actually the dialogue that is different. And the graph here represents 9 different recognizers that participated in a broadcast news evaluation. And essentially, you can see that for spontaneous speech, the percentage of words that we get incorrect actually doubles compared to planned speech. So there's a large number of reasons why that might be. So people tend to put a lot of disfluencies into spontaneous speech. So that's when they say things like and and pause for time. It's very difficult to actually talk about disfluencies because you start noticing them in your own speech and your audience starts noticing them. So all of a sudden you start saying and it's very difficult to recover from that. So, also, as I said, the background acoustics do change a lot. Now, here we've controlled for background acoustics, but as you get more natural speech, you're going to have a lot of difference because of that. But one of the things that I was interested in my thesis is that your pronunciations change a lot when you're talking very naturally, as opposed to when you're dictating a letter, you can be a little more specific with your pronunciations. So I'll come back to that in a minute. But the story that I'm here to tell is basically that there's really no magic bullet. That people have been pushing and pushing and pushing on this problem, and they get small incremental advances in speech recognition. So there's not going to be anything that's going to solve the problem entirely. So how are we going to go about in a field that is very difficult to do that, to solve the problem in one step? Well, obviously it's making incremental steps. And my plan is to take a look at what is actually going on in speech and look at what makes things happen in speech. So for instance, speaking rate can affect pronunciation quite a bit. And then design a statistical model that is based on the things that you've learned in your investigations. Or you can use investigations from the literature and whatnot. I mean, you don't have to go out and do it at your own. But then when you've got these new models, integrate them with your old models. Because it turns out that finding 2 ways of representing something and then combining them into one is often more robust than just using either one by themselves. So don't throw out the old models. Later on, if it comes down to the fact that you find that your old models are not helping you anymore, then you can throw it out after you've added in more information. But usually, combining all these sources of information is very helpful. So my thesis, which really actually started here at Johns Hopkins in some sense at the 1996 workshop, talks about how to integrate knowledge sources in pronunciation modeling. And so one of the things that I was looking at is what actually influences the pronunciations of the words. And so I'm going to talk a little bit about the factors that go into that. But then once you've determined that, how can you integrate these knowledge sources into building a new pronunciation model? So I'm going to talk about 2 subproblems that illustrate the power of combining different representations. And both of these subproblems were actually stuff that I worked on with various people at ICSE and other places. And then talk a bit more about how this fits into the framework of my thesis. So what do I mean by modeling pronunciation variation? I've been sort of just tossing these words out. And we have this intuitive idea of what a pronunciation is. But I want to sort of give you a more coherent understanding of how we do it in an automatic speech recognizer. So the idea of a speech recognizer is that we're going to take in some speech signal and put out some recognized words, right? And what the speech recognizer does is it looks at the speech signal and it looks at tiny chunks of the signal and says, oh, OK, this is a puh, or this is a buh, or this is an ah, or something like that. And the pronunciation model, the job of that pronunciation model is to take those individual phones and combine them together into words, just at a very basic level. And then we have a language model later on that tells us how to combine words, right? So it's a very simplistic view, but that's sort of the game that we're playing here. And it turns out that linguistically, these things are, we've motivated these things as linguistic phones, but it turns out that these are actually statistical models. So sometimes the patterns that we use to put together pronunciation models may not be the same as what we would find linguistically plausible. We hope that they are, but we have to remember that these are linguistic. These are statistical entities and not linguistic entities. So we're not dealing necessarily with what's going on in our own brains. So, but linguistically, things do vary quite a bit. So let's look at the word probably. And generally, people have two pronunciations for probably. One is the full probably, and one is probably, right? And so the statistics that I calculated this are from a red speech corpus. But it turns out that if you look at a corpus of spontaneous speech, where two people are talking over the telephone to each other, that there are actually 21 different variants in this small corpus that I was looking at. And the most likely pronunciation is still probably, but it has a much lower probability. And in fact, the second most likely is one that isn't even usually used, probably, or, in the canonical sense. So the game that we're going to try and play is, given that we know these canonical pronunciations, how can we predict how these new pronunciations can arise, or these actual pronunciations? So what makes this hard is that there's actually 19 others of these. So the tails of this distribution are pretty long. So and it's an important problem to work on because I mean one of your students here, Murat Sarklar, basically showed that if you can predict the right pronunciation, you can have the error rate on the switchboard corpus here, and that was reproduced again by some other people at Dragon. And interestingly, if you have a corpus where you can tell what the linguists have said this is the pronunciation, and if it matches the dictionary, we do a lot better than when we have a pronunciation that's sort of out of dictionary. So it really does affect the error rates. So how do you build a pronunciation model? Well, the simplest thing you can do is go and get a corpus of how words are pronounced. So maybe you have a linguist write these down, or you can automatically generate them. So I'll talk a little bit about how to automatically generate this. But let's say that you had and, on, and ant are the three pronunciations in your dictionary, so representing two words. So if you just learned the frequency of each of these things, you would say that the probability of and the probability on are both 0.5, right? And the probability of ant is going to be ant, with a probability of 1. But you might want to learn the generalization that if you've seen this data, that you might want to predict that you could see aunt, which is a valid pronunciation for ant, at least according to my wife. So what people have done is to learn essentially a phone transformation model, where you say, OK, I have some set of canonical pronunciations, and I'm just going to say that and has a pronunciation and ant has a pronunciation ant. And according to this corpus, I can predict that this a will be realized as 33% of the time, and 67% of the time it will be right? Once you cross-multiply the corpus, then you can generate this new pronunciation for aunt. OK. So obviously, you can generate you can use a different set of context to make the statistical transformation more context dependent. So you might say, oh, if this a occurs at the beginning of the word and the next thing is an n, then I'm going to have a probability for a. So one of the games that we're going to play is how do we determine what factors can go into this context. But another trade-off that you have is that maybe the fact that there's a lot of variation for and is specific to the word and. I mean, and has a very specific status in our language because it doesn't act the same way as the noun ant, right? It's a conjunction, right? And so we see it very frequently. It has a different part of speech. Maybe we want to be learning word-specific information about these things. So the question is, there is this trade-off between learning on the phone level and learning on the word level that needs to be investigated quite a bit. So the three main issues, just summarizing, is how do we get a corpus of these pronunciation alternatives? We can start with having a linguist go through and transcribing the corpus, or we can use a recognizer to generate alternatives. And these other two things that I touched on, which are, what are the features that we should be looking at to determine how this transformation occurs, and what level should we be looking at? So let me give a quick overview for people who don't know all the statistical models that go into a speech recognition system. Essentially, we have three different models. The pronunciation model is just one of these three models. So essentially, we put out the problem of what is the most likely word sequence given some acoustics. That's what a speech recognizer wants to determine, right? So we'll represent a word sequence as M and an acoustics as X, okay? Now, the way we break down this problem is we say, okay, we'll learn statistics for individual phones and then find out how we can combine phones into words and then how we can combine words together. So that we break these things into three different models. And essentially, then you just do a search over these things. So the three different models are the language model. So usually, this is a probability over the word sequence. And what that, in essence, is just usually an n-gram model of essentially a Markov chain of these things. Now, you can get into more complex language models. And for instance, Cyprian from your department actually does this quite nicely, is look at different ways to investigate that kind of thing. So the pronunciation model is this other thing that tells you how do you combine the phone states into making words, right? So we'll talk more about that later. But what I want to concentrate on at the moment is just this acoustic model that says, given a little chunk of acoustics, or given a particular phone, what is the likelihood that I've seen this chunk of acoustics? Now, there's a signal analysis part that basically takes the speech waveform and turns it into a vector of numbers. And then what we do at ICSI is to have a neural net that actually computes the posterior probability Q given X. And then what we do is we actually divide by the priors to give us a scaled version of this P of X given Q. So we're off by a factor of P of X. But essentially, this is what gives us this chunk of predict. How do you say this phone is likely given this? These acoustics are likely generated by this phone. So I'm going to talk a little bit about how we generate these things and how we use combination to improve this acoustic model. And this actually comes in relevant later for the pronunciation modeling because they depend on the acoustics. Oh, I'm sorry. Let me go back here 1 second and say I was going to tell you how we actually generate the best phone sequence. Well, essentially, if you just ignore this model here, and do a search to maximize the best phone sequence instead of the best states, instead of the best word sequence, then you can actually generate a new phone string. And that gives you an idea of what the acoustic models are seeing at a particular time. So this was something that we did in conjunction with some people at Cambridge and Sheffield in England as part of a project for this DARPA broadcast news evaluation. Now, the important thing to know about the broadcast news scenario is that there are focus conditions where you break down and you say, okay, this type of speech was read by a newscaster, or this was a spontaneous interview. And so we have test sets that are demarcated by this information. And these guys at Cambridge and Sheffield were doing very well on these newscasts, but they were not doing very well, in particular on the telephone bandwidth models. So what we wanted to do is find a way to build an acoustic model that would maximize the difference with their model, but and so may not help we don't necessarily want to improve the newscast scenario, but we want to improve these other scenarios that they don't do so well in. So how do we do that? Well, since we basically didn't have these models take up a long time to train up, we basically decided to go whole hog and throw in a whole bunch of differences with their current system. So they have a standard analysis technique, which is called perceptual linear prediction, if you're interested. They have a particular type of neural network to compute the posterior probabilities called the recurrent neural network. Our system has three major differences from theirs. One is that we used what's called the modulation spectrogram filtered features, which is essentially a temporally sluggish analysis. This was designed by another PhD student in my lab. And the idea is that when you have reverberation coming off the walls, that makes the acoustic signal very temporally sluggish because you get a lot of echoes coming back. And this analysis technique is useful because it matches those characteristics. The other thing we did is we downsampled the entire data set to be telephone bandwidth. So usually speech has a really wide bandwidth. Coming off the radio, I guess it goes up to 5,000 or 6,000 kilohertz. But over the telephone, if you notice, sometimes you have different difficulties between Fs and Ss. And that's because the acoustic energy that differentiates Fs and Ss is above 3,400 kilohertz, which is the cutoff threshold for that. So, given those two things, and also we had a different neural network configuration, we built up another model in parallel to theirs. And then we have a probability combination technique that basically looks at finding some way to combine these two things. So the plus there is actually not a plus, but rather some combination function, right? So we looked at a number of different combination functions. The dumbest thing you can think to do is to just take the two probabilities, add them together, and divide by 2, right? That's averaging. That's what we call averaging in the linear domain. It turns out the best thing to do is actually averaging in the log domain, which is essentially multiplying the two probabilities together. We had another student who looked at combining things with the neural network and other combination techniques, and it turns out that the gain that you get from putting in all of these more complicated combining functions is very small compared to the overall improvement that you get just from doing average log domain. So I should introduce the concept of word error rate. I've sort of alluded to it before, but essentially the word error rate is the number of times that you get something that was actually said wrong, plus the number of times that your speech recognizer puts in a spurious insertion. So the interesting thing is that we do get a nice improvement from adding the two models together, but it wasn't from the planned studio speech. So the things that we were actually targeting is where we actually did better. So that says if we can focus our representations to be good for the problem conditions, we can actually do better in the problem conditions. Notice we haven't solved the problem, because if we'd solved the problem, at least made these things invariant, then these two numbers should be roughly the same. So there's still more to do. So the next thing I'd like to talk about is what features should be part of this context. The corpus for pronunciation alternatives we generated using this combined acoustic model, which has specific properties that are tuned towards telephone speech and reverberant conditions and whatnot. So, and that will come back to play later. But now we should talk about how do we generate these new how do we better predict how these alternatives are going to occur. So one thing I sort of alluded to before was that speaking rate has a significant effect on pronunciation. So people walked up to their friends and said, "Did you eat yet?" And of course, you recognize that that's, did you eat yet? Right? But we don't have to necessarily pronounce things in full. So we get a lot of reductions going on in spontaneous speech. So one way to look at to quantify how these things occur is to define metrics that tell you how different is one pronunciation from another. So I defined a syllable pronunciation metric that basically says, well, if you look at the difference between can and cam, right, that's going to be a lot different than can and ma'am, right? So, so you want a metric that basically says, how different are these things? And essentially, I looked at phonetic features for anybody who's interested in the actual metric. But the point being that if you look at speaking rate on this axis and the distance between two syllables, the phonetic distance, you can see that there's an incredible effect across. So this is again for the switchboard corpus. So so speaking rate is definitely something that we need to know about, but how do we estimate it? Now, we can go through and calculate the number of syllables per second. Now, you may be wondering why I don't use words per second. It's because if I say things like anti-disestablishmentarianism, right? I said that really fast, but there's only one word in there. So you want to be counting syllables per second because it gives you a much more even measure of things. You could also use phones per second, but if you tend to have a lot of phone deletions, that's going to undercount the number of phones. So syllables are a good trade-off between those. And essentially, this is using data that was transcribed at ICSI, where they demarcated syllable boundaries and then gave us the phone identities for these things. So it's nice if you have a linguistic transcriber to tell you where these or the syllable marks are. But the problem is that if you don't have, if you want to run a speech recognizer, you can't exactly hire a linguist to go and transcribe all the syllables as the output's coming from the speech recognizer, right? So you need to have some sort of automatic way of generating these things. So you could use your recognizer to generate a hypothesis of how many syllables were there and then count. But it turns out that that tends to undercount the syllable counts a little bit, especially when you're getting words wrong a lot. So my advisor, Nelson Morgan, and I were working on ways to look at speaking rate directly in the signal. So for instance, if you see here, this speech signal has clumps of energy that correspond to each of the syllables. And the idea is that if you can detect where those clumps of energy are, then you can and how many clumps are going by per second, you can get a signal processing estimate of the speaking rate. It's not necessarily an easy task because here we have two syllables, but it's difficult to tell that there's two different clumps. So I'm not a signal processing person myself. And basically, my advisor looked at three different ways of looking at the speech signal. And essentially, they boil down to whether you look across this entire frequency band all at once, or you look at subparts of the frequency band and look at the modulations in that. And whether you do this counting in the time domain by saying, OK, count the number of peaks per second, or you do it in the frequency domain and you get a spectral moment. So he came up with three different ways of looking at this. And what I was interested in is, can we combine the information from these measures to improve the accuracy of over any single one of them. So here we have the 3 different measures that he was using. And essentially, the x-axis on all of these is the true number of syllables per second according to the transcribers. And the y-axis is the estimate given by each one of these individual things. And you can see that they're doing different things, mostly depending on whether they're doing the spectral moment or the peak counting, right? And it turns out that if you have some combining function, you can actually improve the correlation slightly over the best one, which is the subband peak count. The interesting thing is that what actually does the most, what actually helps the most, is adding in this other thing that looks most different. So it really, again, seems to be combining different things. It gives you a more robust estimate. Now, you may wonder what that combining function was. Well, the dumbest thing you can do, of course, is each one of these corresponds to a single number. You average the 3 numbers together, and you get another number, right? So that's the dumbest thing. Then the next dumbest thing you could do is you could take a weighted average of those things. So you learn, you get a training set, you learn the weighting function for all these things. Turns out the weighting function is almost exactly even for all 3. So you can, I also looked at doing more complex things, but you can't really improve things that much over the very simple combining techniques. So it seems that, at least for these domains, that the simplest combining techniques work well. It's just really, can you find different representations? So now I'm going to get into how to build these models. And so basically, the main thing that I'm concerned about is, now that we've got things like speaking rate estimations, what are the appropriate things to add into a model of how you can pronounce, say, a word in a particular context, right? So one thing that I noticed early on, and actually this was a shared observation with Murat, who I was working with for a while on this, is that speaking rate and word predictability both affect pronunciation. And the interesting thing is that the effect is actually slightly nonlinear in that this axis represents words that are more likely. This is the speaking rate axis. Again, this is the syllable distance metric. So if you took the graph that I saw before, it was just a projection in this direction. Okay. It turns out that the words that are the most likely are the ones that are affected by speaking rate the most. And you can see that this slope here is different than for over here. So, but there's still an effect of speaking rate in this area, and there's still an effect, in this direction for unigram probability. So, but it says that there's a significant interaction between these features. But what that says is that we should be changing our pronunciation model dynamically based on these features. And this is an argument that we've been making for a while, where you might have a, you might change, if you've noticed all of a sudden, oh, this guy is speaking fast, I might want to add some more reduced pronunciations into our model. So looking more at the data in the switchboard corpus, it became obvious that phonetic context is really important. That you can't actually just look at the speaking rate and word predictability, because the interactions on individual phones are really context dependent. And so these things tend to be secondary. The speaking rate and word predictability tend to be secondary to the phonetic context. Okay? But the other thing is that if you look at, traditionally, phonetic context means look at the phone to the left, look at the phone to the right. Maybe you could look 2 to the left, 2 to the right. But the pronunciation statistics of individual words that were phonetically very similar can actually be very different. And so there seems to be some lexical information that is very important to the way words are pronounced. So, so that speaks to, that's why I got into building syllable and word models, is to try and add in some of this context while actually adding in some lexical specific information. So the question is, what features should we be using? Well, the traditional context that I was saying, what's the phone to the left, phone to the right. But one of the things that we did here at Hopkins is to include things like what's the syllabic position of the phone to the left. So, is this at the end of a syllable? Is this at the beginning of a syllable? Because it turns out things at the ends of syllables tend to be deleted more. What's the stress of the syllable? And you can start getting to things like what's the identity of the word to the left? So if I learn going in to, if I learn the pronunciation of to, or the pronunciation of going with to the next side, you might predict Ghana a lot more likely. So this essentially gets into the idea of multi-word models, and it sort of subsumes the idea of multi-word models into the same framework that has been used traditionally on the phone level. And then, of course, I'm interested in including these extra segmental features, such as speaking word predictability. One interesting thing was the time since last pause. I just stuck it in there because I thought, people get tired near the ends of their sentences, and maybe they're pronouncing things not very carefully and whatnot. Turns out it's exactly the opposite way around. That when you get towards the ends of a sentence, people pronounce things a lot more carefully. And that's because people tend to put new information at the ends of sentences. So they tend to front load with stuff that's very predictable, and then they'll give you, wham, here's the new information at the end. So it's one of the nice things about this thing is that we can actually learn about the linguistic, we can find linguistic phenomena that we're not expecting by analyzing this data. Let me see how I'm doing on time. Oh, I gotta. Okay. So the particular statistical model that I'm using to determine these pronunciations is a decision tree. Now, essentially what we do is, and this is particularly the framework that we came up with at Hopkins, is given a particular canonical pronunciation, let's say of E, so 5-year-old, maybe I pronounced it at yer there, okay? And I learn with a context window, I have a particular set of features that correspond to this transformation E to right? So I can build the decision tree that essentially greedily goes through the features and tries to find the most likely, the thing that makes each one of these leaves as pure as possible in a statistical sense. For instance, I might learn that the most important thing was whether this phone was stressed or not. And maybe the next thing is this thing to the left of it a coda? And at each of these leaves, I'm going to have a residual probability distribution over each of these phones. At the word level, this gets to be a little more interesting. So this is an example tree for the word them. And it turns out that in this corpus, I had 3 pronunciations for them. Essentially them, which is sort of the standard pronunciation, and them, which is more of it's a reduced pronunciation that you would find in fast context. And then maybe thun, which unfortunately is very confusable with than, right? So we don't want to just throw the pronunciation for thun into the dictionary, but we want to find the context in which it's actually appropriate. And in fact, as you can see by this yellow box, the most likely places where these occur is if the next phone is going to be a D or a T. And essentially, that's in linguistics known as a place assimilation. So the moves back to an n because it's in the same place as a d in terms of where your tongue is. So it's nice that there's a linguistic motivation of these things. And it also, we get very low probability of thun in the other parts of the tree. So this says it's only in these contexts that we should expect these kind of things. Now, one of the problems, I'm using cart-style decision trees. And one of the main problems with this type of thing is that there's no interactions between these features. So I would not be able to predict the kind of things that I was seeing before with the speaking rate and word predictability, because you would need to be able to take account of both features at the same time. So there's ways to work around that in decision trees, but there's also other statistical models that we might want to investigate on this kind of thing. But essentially, I wanted to get my thesis signed, so I didn't go down that track. The nice thing about cart trees, though, is that we can see which features are important and which features are not. So here's a set of experiments that I did with these pronunciation models. So in the first model, what I did was I trained up 56 different phone decision trees using this broadcast news corpus that was automatically generated by the good acoustic models. And so there's about 200 hours of training data, which gives us a lot of training examples. And what I did was I actually used these trees to retranscribe the corpus. So this was a technique that was developed in '97 here at Johns Hopkins. I guess it's probably been used elsewhere. But essentially, you can use the decision trees as in the same way that you would use a language model to constrain the particular word sequences. You can use this as a way to constrain potential phone sequences. And the reason why it's sort of a smoothing function is because the decision trees are actually pruned back so that you don't get all of the possible examples that you saw in the training corpus. So once you have this retranscribed corpus, you can do the simple counting techniques that I talked about at the beginning to get a new static dictionary. The second model I looked at basically trained, based on this retranscribed data, 800 word decision trees based on this corpus. So one thing I wasn't sure about is whether these trees would be effective with or without the extra segmental features. And it turns out, so I trained trees with both the features and without the features. And it turns out that when you look at a held out test set of pronunciations, including these features actually does improve prediction, but it's the least helpful thing in improving prediction of pronunciation. Then I use these decision trees in a dynamic dictionary for rescoring. And so what do I mean by a dynamic dictionary? Well, essentially, this is sort of the abbreviated version of the model that I showed at the beginning. We have this pronunciation model that basically says, this is what this pronunciation of this word was. You can use the decoder to generate, instead of generating the best hypothesis, you can say, OK, I'll give you 100 guesses, or I'll give you 1,000 guesses. And so you get a list of all these different hypotheses. You can also get a word graph and decode in that manner as well. But I don't want to get into that. And essentially, the dynamic pronunciation model says, OK, let's look at this particular word was. And what is the particular word context that it occurs in? And what's the particular phone context that it occurs in? And what's the speaking rate? And then we use the decision trees to ask, OK, here's the context. What is the appropriate set of pronunciations in this situation? So you get essentially two different scores depending on whether you use the static model or the dynamic model. And we separate out the language model score as a separate thing because you can speech recognizers often trade off between these acoustic model scores and these language model scores. So we might actually, if we predict that under this dynamic model something is a lot less likely, like the most likely static hypothesis, then we might actually say, OK, that's not the best hypothesis now because now all of a sudden this new hypothesis looks a lot better. So in the interest of always doing combining, right? I looked at combining these hypotheses that are coming out of the recognizer. And it turns out that when you just use the one best hypothesis from the static model and the word trees, that you get actually the same exact error rate. And that was kind of discouraging at first. But then I realized, I mean, you're still getting about 0.5% over the unimproved dictionary, which is OK, but you're not terribly excited about that kind of thing. But it turns out that when I did an error analysis of what's going on, they're actually doing different things. The hypotheses that they're putting out are not exactly the same. And it turns out that it has to do with how robust the particular word trees that I was looking at are. Sometimes they do a very good job at predicting things, and sometimes they don't. So if you smooth by adding these two scores together and doing a weighted combination, you actually get about another 0.5% win again. So you get the same gain again. Now, if you do, so that's just saying, that's just taking, do I take this line or do I take this line as my guess? And if you do more intelligent combination where you're looking at the confidence of each system in particular words in the hypothesis, then you actually do about the same. But I'm sure that Lydia from your department would have a lot more to say about this, because this is exactly the type of thing that she's interested in. But the point is that it seems that the simple combination techniques are working, again, the best. That doing smarter things is not necessarily the best thing to do. One thing is that this was optimized on a held. This is the optimization on a held out set. And it turns out that the trees that were working the best were the ones that were without the extra segmental features. So, which was a little disappointing. So there seems to be this disjunct between essentially what language modelers would call perplexity results, improvement of prediction on a test set, and performance in a speech recognizer. And I think we need to understand that a lot better. And I certainly don't understand that fully. So once we've got all our tuning done, we evaluate these things on an independent test set. And essentially, I looked at the three dictionaries that I sort of talked about before, where I use this. You have to remember that all these are done with this the combined acoustic model that is optimized for the telephone speech. And what's interesting is that we don't actually get any gain when we're looking at the planned speech. In fact, so lower numbers are better, remember. So we actually do slightly worse here for the planned speech. But on spontaneous speech, we get sort of the standard 1%. But where we're actually improving quite a bit is on the telephone speech. And that's interesting because there seems to be some synergy going on with this new acoustic model that's tuned to this particular condition and the pronunciation modeling. So I'm picking up on some regularities that are going on in this the acoustic model. So here's sort of where I am to date. Basically, I'm very interested in finding out new things about speech. So for instance, the rate and word predictability interactions was something that came out of my thesis, right? And then once we find out these things, we integrate them into the statistical models. And the thing that I find interesting is that combining these things with older models that do OK can improve the robustness of both. And that's the main message of this talk. So we see that doing this in several different domains gives us a small reduction, but an incremental step in various domains. So the question is, the simplest combinations seem to be working the best. And I think there's a lot of questions about whether more motivated combination techniques might work better or not. I don't know. It may turn out that it's just really getting different sources of information. But the nice thing about this sort of paradigm where we look at a particular subproblem within the problem that we're looking at is that we can target performance improvements in where we're not doing well. So that speaks to things like boosting and whatnot, where you target your performance in a way that helps you where you're doing poorly. I don't want to talk about the last point, but I want to actually go on to where do I think this should go? Well, I mean, everybody sort of knows that there's this list of things that you wish that you had done in your thesis, right? And so obviously, I alluded to the fact that I'm not particularly happy with the non-interactivity of features in the cart trees. And so I think that's an important thing to look at. And there are other paradigms, such as phonological rules, which seem to be getting a slightly better improvement than the improvements that I'm getting. And so the question is, the phonological rules sort of pre-specify what alternations you might see, and I'm sort of inducing them directly from data. So is the difference between those two paradigms, an important one? So another thing is what I call the perplexity problem, and I really would like to know why it is that improving prediction doesn't actually help improve the error rate. And part of it is that these systems are very complicated and there's a lot of interactions going on between the models. But one has to wonder if perplexity is the appropriate paradigm to be looking at these types of things. One thing I'm very interested in now is sort of going down the idea of of combining information sources is people just basically say, OK, when do these things agree? And combine things in ways that look at when sources agree. But sometimes, if you have a telephone bandwidth analysis here that's going on, sometimes you're going to get phones that look very different. So you're going to think, oh, this thing's going to think, oh, no, this is an F. And maybe the standard analysis is, oh, no, that's an S, right? And there may be information in when these sources actually disagree. And I think that's an important thing to look at. Sort of in the longer term, I think we really need to know a lot more about spontaneous speech. I think we just don't understand the problems that make it different from planned speech. A lot of studies that go on in linguistics departments are based on planned speech, and they're valuable up to a point. But there are specific phenomena that are going on with spontaneous speech that we need to investigate further. So, and I think that the small improvements that I got in these pronunciation models, can be a little disheartening. But I think we've seen that the pronunciation models can be a good way to improve the error rate in sort of independent studies. So I think the answer is we just don't have the right model yet. Another thing that I think is very important is starting to look at ways to integrate natural language understanding and speech recognition. So one of the things that I noticed here is that the predictability of the word really does influence the pronunciation of the word. And that's, the measure that I was looking at, which is essentially the language model trigram probability, is really, in some sense, a very dumb measure of predictability. It's strong in the in terms of local context, but in terms of predicting when particular nouns might be occurring given a topic or something like that. If you had topic-based language models, maybe you could be doing this better. But I think there's other levels at which we could be looking at natural language understanding. And I think one of the interesting things is that when we do speech recognition word error rates, we're treating all words as equal, but it's clear that not all words are as important as others. And can we find ways of determining which words are the important words and if we're recognizing them correctly? So that's going to be somewhat task dependent. So it's, in an information retrieval context, maybe it's the keywords that are important. So I think we need to start looking at natural language understanding to basically guide us in terms of how we should be building our speech recognition models. There are other cues that can be used to indicate, which of these things are prominent words and which words does the speaker think are important. And I think we need to do a lot of work on that, and that's a direction I'm interested in heading. I'm again interested in I don't have a bullet point up here, but I'm interested in this combining idea of different information sources. So I'm interested in it from the viewpoint of these particular language tasks, but I think it's a general problem that really needs to be addressed more. Finally, I think that we really need to be working on the interface issues a lot more. And I'm very interested in knowing, working with people to try and figure out how we can use speech as a component of these, with these HCI issues. And I think it's something that people have sort of swept under the carpet of like, oh, we'll just get a speech recognizer. But we have speech and natural language issues in terms of, how do we tailor our things to specific applications to make good interfaces. So that's all I had to say, and thanks a lot.
When you have your, when you combine the system linear, when you have the linear interpolation, the weights depend on the context of all, or if they were just...
The weights, so when I was looking at those systems, the weights did not depend on the context, and that might be something that's, I mean, you meant the static dictionary and the dynamic dictionary, right? Right, okay.
Might this be a reason why your weights were almost equal?
Could be. I think, well, so when I was combining at the word level, I actually used a more complex metric, which was essentially how confident is the recognizer in this particular word. So that gives you some context dependence. So essentially, the recognizer can output a number between 0 and 1 and says, what's the probability that I have this word correct, right? And so there are standard techniques called, well, one of them is called Rover, that essentially votes between all these things. And so that's one way to combine that has a weighted factor to it, and but it doesn't. But that particular metric didn't improve things. So I'm not saying that there isn't a metric out there, but it isn't any of the obvious metrics. So.
The fact that more predictable words are more prone to pronunciation was very aggressive. Isn't it intuitive? Because a speaker tries to emphasize words which are not obviously coming after.
Sure, it's intuitive, but the thing is that, I mean, having something that's intuitive and having something that you can show with data is another, two separate things. But yes, I mean that's why we investigated in the first place. Is that we said, oh, of course, people are going to say something more predictable. They're not going to say it as carefully. I mean, there's information theory arguments about why that should be, right? But so. I think the answer is yes, we found that it is an intuitive reason to look at it, and then we looked at the data, and yes, in fact, this is the case. Right.
Yeah, I'm not in this area, so I don't know much about it, but just if you look at your statistics, between the improvements you're getting here are so small, I was worried like there's a lot of potentially you're seeing noise.
Right. So the way that we look at these things is we look at very large data sets to compute these things. So the numbers, going that 1%, that full from the original dictionary to the combined system is actually statistically significant using a binomial difference test.
I mean, it's
But
significant, but I guess maybe statistically significant in that sense, but in terms of significant in the sense that you care about it.
sure.
I'm wondering the numbers are so small.
Yeah. I mean, it's an issue, and the thing. I actually have a slide that addresses this. Let me see if I can. I mean, let me put this in the context of the way other people have been looking at this problem. So this is the difference between the 1996 system and 1997 system for one site that actually looked at the difference between these, what each of these steps that they did worked on. So this is, essentially 8 people working full out for a year. Well, probably not full out for a year, but full out for several months on this stuff. So this is, several person years of work. And they're looking at different techniques. And a lot of these actually, are techniques that they've borrowed from other groups. So they're proven in other things. And essentially, you can see that going from a word error rate of 46 to 34% was made in several steps. And the relative improvements here are all, pretty small. So you get some absolute improvements here that are pretty large, but you're starting out with a much higher error rate. So my model is essentially looking at, roughly 4% improvements here and 12% in this particularly focused condition, which is about the same as other things. So, and these people are, have been known to be really good. So, I mean, the point is that it's because there's so many different interacting modules, it's hard to know whether something that you do is going to pay off in some other situation. And part of the problem is that if you're not doing if you don't have a state-of-the-art system, people will often say, well, maybe that's a fluke, and so people don't necessarily always pay attention to your results. But the point is that nobody. I mean, it's very rare when one of these things that is such a great idea that works out and really pushes the error down quite a bit happens. So I would say that this is sort of in the realm of in the middle realm of improvements, right?
So I think we can borrow a lot of ideas from speech synthesis.
Uh-huh.
So in speech synthesis, we care a lot more precise parameters. So do you think it will be useful in your models such as speech?
In speech synthesis, you use more. I missed the word.
I mean, in speech synthesis, the precise model is more complex.
Yes.
So we not only care about duration, we care about the pitch, the style, or things like that. So do you think these parameters can be helpful to pronunciation models recognition?
I think so. Particularly duration is an important thing that's is ignored. But I think pitch. I mean, so that's one of the things that I was sort of alluding to before. With if you notice that you have a pitch emphasis on a particular thing, you might know that people are stressing that, and therefore, are likely to get a full pronunciation. And if they're not emphasizing something, then they're likely to be, it's likely to be old information, and they're going to be reducing pronunciation. So that's, I think, something that should definitely be looked at. It would be great to know what the relationship is between pitch and pronunciation. So I'm very interested in that particular area.
So I was wondering, the statistical model for building words out of different sounds doesn't seem to take into account much global information. For instance, if one person has a particular dialect, then if some particular pronunciation of one word is more likely for this person, then there's probably this whole set of other things you can know.
Yeah. I think it's certainly true, and there are some people out there who do that kind of work in terms of Jason Humphreys built some models of particular accents in his thesis. So this was a guy from Cambridge, but I don't think that that's been fully explored. Part of it is that, I mean, looking at the particular tasks that have been done at this point, people often adapt things to pronunciation models to specific people, or actually they adapt the acoustic models to specific people. So it takes account of some of that stuff, but I think that we could, if we could, I mean, I could imagine a scenario where you're learning things with a hidden variable that represents the accent or something like that. So you accumulate enough data over time, and then you say, oh, this person really has a southern accent, or is from Boston or something like that. And you could imagine building that data up over time. Nobody's really looked at that particular type of model, I don't think. So I think it's a perfectly valid thing. Part of the problem is knowing that once you have that information, what does it mean in terms of the actual pronunciation productions? I don't think people have a great handle on that.
I only brought it up because you talked about having a dynamic model of the statistics in terms of very local context.
Yeah.
And this is sort of trying to add a more global context.
Right.
To,
Yeah, I mean, obviously I'm more interested in the global context than the local context in terms of, I mean, I was very excited about the speaking rate thing because, I mean, it's, again, a global context thing, right? I mean, it's not as global as the accent, but, you know, it's another level. And I think if we need to think about how these levels work together, that we can get, so that we can get this higher level information down lower into the recognizer.
Just have one more question. Do you have, you're interested in HCI kinds of things. Do you have an appreciation of what kind of rate is adequate for certain tasks? And in particular, you're doing global rates, and you may be doing worse in words that are less important.
Yes.
Right, so I mean, you might be able to pose the whole situation better if you say, well, for this kind of task, this is the rate we need on these kinds of words.
Yeah, I don't. Oh, go ahead. Sorry.
Sorry, no, that was.
No, I don't think people really know. And I can give you anecdotal stuff. One of the things that the people who've been doing this broadcast news type tasks have been doing with this data is essentially audio data mining, where you go out and you collect a bunch of TV or news transcripts and you go and you recognize them and then you try and do information retrieval on those things. And for that task, it turns out that having error rates of 30 to 40% don't matter. That you actually can do pretty well even if your models are doing pretty poorly. Of course, the better you do, the more words you get right, the better you are. But nobody has really looked at this idea of which words are important or not, as far as I know. I mean, I could be putting my foot in my mouth right now.
Some
But
models may have more improvement in understanding real keywords instead of just
yeah,
suppressing the overall error rate on things you really don't care about. Right?
Yeah.
Some of your stuff.
right, yeah. That's what you would hope.
Great, well, thank you very much.
Okay.